Section 1.8 is about working with functions. So what we'll do is we'll build models, specifically mathematical models, from a verbal description of the problem. A mathematical model, as I've written here, represents a real-world situation and allows us to answer questions about a physical system and or make predictions about the future of it. So that's why they're important to use for physical situations. We will start with linear models. This example, what is the cost of renting a bicycle if it costs $1 to rent it and $2 for every 30 minutes that you ride it? This should feel a lot like some of the examples we've already done because this course I always try to drive it with context and physical examples. So we have a linear model, and first thing we need to decide is what is x. And so if x is going to be represented in increments of 30 minutes, because it's $2 for every 30 minutes that you ride it, so even if you rode it for 20 minutes, you're paying for 30, effectively. So we'll say it's in increments of 30 minutes, or a half hour, whichever is easier for you to consider. Now the function, your default is always f of x, but that's just because you're saying a function of x. Now when we talk about a physical system, we typically name the function something that relates to the system. So in this sense, we are calculating the cost of renting the bicycle, so it's natural to make the function name c of x, and this is the cost of renting the bicycle. Since this is a linear model, we are looking for a constant and a rate, right? The constant in this case is the cost that you pay no matter how long you ride it, which is the cost, the $1 to rent it. And the rate, right, it's $2 for every 30 minutes. So for each increment of 30 minutes, you pay $2. So you can define c of x as equal to this $1 plus the $2 times the number of 30-minute increments. And so if you write it even for a minute, that even though that's only 1 minute, you're paying for 30 by the way this model is set up. And so that gives us $1 plus $2 times x, or to simplify just the form, you can write that as 1 plus 2x. Just make sure that when you write your final answer, it's still in dollars. Now that we have the equation, we can answer questions about this model, just like we did in the previous sections, where, say, I want to know what is the cost of renting this bicycle for 4 hours. How many half-hour increments is that? So 4 hours divided by a half hour, because that's in hours, I'd rather use the half hour for that. And so 1/2 hours gets me, right, that's going to get me 8 increments of 30 minutes. Which means that when I substitute it into my function, I'm not taking c of 4, I'm taking c of 8. So I have 1 plus 2 times 8, getting me 16 plus 1, or 17. Now remember, that needs to be in dollars when you write your actual answer. So it costs $17 to rent the bicycle for 4 hours. An alternative question you might be able to ask is, how long can you rent this bicycle for $10? In this problem, you are actually going to be doing the opposite. You're not plugging it into the function, you're solving the function for when x, what value of x is going to get you an output of $10. So when is my cost equal to $10? Now, c of x, I can just put here on the right-hand side, right? That's $1 plus $2 times x, so that I have my units sort of in the equation already. Subtract the 1. You have $9 is equal to $2 times x. Divide by 2. Now, since both of these have the dollar unit, that reduces, that unit can be gone after this point. So I have 4.5 is equal to x. Now, remember that x is increments of 30 minutes, so this is 30 minutes or a half hour. I'm going to use a half hour here because I'm going to take that half hour and I'm going to multiply it by 4.5 to get the number of hours. That you can actually rent it. So 4.5 times a half gets us 2.25 hours. That's how long you can rent the bicycle for only $10. The last thing we'll talk about is getting information from the graph of a model. So we'll start with another example here where we have to construct the model and then we'll graph it in order to evaluate it. Now, find the model for the volume of a rectangular container. In this case, the height is equal to x, the width is equal to x, and the depth is equal to 2x. So I've drawn the box for you, and then recall at some point you probably learned that the volume of a box is going to be given by the height times the width times the depth, which in this case is going to be x times 2x, or 2x cubed. So one thing that's nice is once you have this, you can plug it into your calculator to look at the graph to answer some of these questions. But since, just in case, let's real quick review that. X, y, if you were to plot by hand, you can pick values. So I always do -2, -1, 0, 1, 2. If I can substitute all those values in, that gets me, right, you can pick these x values anytime that you build a table. You can pick the x's to be whatever you want them to be. And then you just substitute them in. So a -2 gets me a -8 times 2 gets me -16. -1 cubed is a -1 times a 2 gets me a -2. 0 gets me a 0. 1 gets me a 2. And 2 gets me a 16. So given the axes, now I can substitute these points in. And at -2, -16, that is way off the map, so I can't even put the dot down. But I know that it's way, somewhere probably down in this range, realistically. The -1 is -2, puts a dot here, so I can attempt to connect those guys. But really, I can just put an arrow here, and then I can erase the rest of that. It's unnecessary. It does pass through 0, 0. It passes through 1, 2. And then the 2, again, is going to shoot way up the y-axis. So I'm going to have a similar situation where it's just going to go off there. Once we have the graph, ideally you should be looking at the graph on your calculator right now as a comparison. But you can find this information using the graph, or you can find it also with the equation. If the width is 3 meters, find the volume, right? If the width is 3 meters, and you take a look back at the shape of the box, then the width was equal to x, so v of x, which is the function that we defined, which is 2x cubed, I would just be substituting in 3 for x to get that. So I would have 2 times 3 cubed. 3 cubed gets me 27. 2 times 27 is equal to 54. And then the units do matter. So given the fact that I have a meter times a meter times a meter, right, that's what's happening inside this x cubed, I get meter times meter times meter. That's the same as meter cubed. Alternative question, what are the dimensions of the box if the volume is 128 meters cubed? So in this case, we're trying to figure out what x is, so we can define the dimensions of the box, given that the output of our function is 128 meters cubed. Again, if you have it on your calculator, you're searching for an output or a y value of 128 meters cubed. So v of x is going to equal 128 meters cubed in that case. And if you were to do this algebraically, you would say this is equal to the 2x cubed for our function, so you divide by 2. That gets you 64 is x cubed. And in this case, if you take a cube root, the nice thing about an odd root is that it will get you back the same sign that you have. So, of course, we're talking about a physical thing. It should be positive anyway. But if you take the cube root of 64 in your calculator, you should get a 4 back. 4 is equal to x. And remember that this was meters cubed, right? The 64. So when I take a cube root of a meters cubed, I get a meters back. So 4 meters should be the value for x, which means that when we look at the picture of our box, that our height is equal to 4 meters, our width is equal to 4 meters, and our depth is equal to 2 times that, which is 8 meters. And those are the dimensions of the box, given that the volume is 128 meters cubed. Last question, when is the volume going to be greater than 16 meters cubed? So first, to figure out when it's greater than 16 meters cubed, you have to determine when it's equal to 16 meters cubed. So the question is asking, when is v of x greater than 16 meters cubed? But to define that, we need to find, okay, well, when is v of x equal to 16 meters cubed? Now, luckily, we did that in the table, right? And we got 16 meters cubed when x was equal to 2 meters. Now, since we got that from our table that we had, we can use that to our advantage. So it's equal to it when x is equal to 2. And given the shape of the graph, which I'll scroll up, you can see that it only goes up from there, right? So it's going to be greater than 16, anything to the right of x equals 2. So we can define the values for when v of x is greater than 16 to be when x is greater than 2 meters.